an extremely useful rule in calculus, which is called L'Hopital's rule, which helps us calculate limits that we couldn't otherwise. So what L'Hopital's rule allows us to do is allows us to calculate limits that would otherwise end up as 0 over 0 or infinity over infinity. One example is the limit as x goes to infinity of x over x squared. If you use L'Hopital's rule, you can find that it goes to 0, but if you just plugged in infinity to the top and bottom, you'd get infinity over infinity, and that's not a definite answer, and that's one of the conditions under which L'Hopital's rule applies. So this is the rule. The limit as x goes to c of f of x over g of x equals the limit as x goes to c of df dx divided by dg dx, or limit as x goes to c of f prime of x over g prime of x. I put both notations. And this rule only applies, and this is really important, it only applies if f of c over g of c would be 0 over 0 or infinity over infinity. If it's not that, and it's not 0 over 0 or infinity over infinity, when you just plug in c, then this rule does not apply. So let's do some examples. Okay, the limit as x goes to infinity of e to the x over x squared. So I'm just going to show you here on the side, just for this one problem, why if we just plugged in x over infinity, x goes to x is infinity, it would not work. We would get e to the infinity power over infinity squared. We're just plugging in infinity for x if we just wanted to use the plug-in method to solve the limit. And doing this is just e to the infinity is just infinity, and infinity squared just infinity. And this is infinity over infinity, and that is one of our conditions here, and this rule applies. If we just plug it in, we just get infinity over infinity. So this means we can use L'Hopital's rule, and we can differentiate, or with respect to x, just take the prime of the top and the bottom, and what we get is e to the x, the derivative with respect to x is just e to the x. Every single derivative of e to the x is just e to the x. It's too strong for differentiation. Okay, x squared prime. The 2 would come down because of the power rule, and then 2 minus 1 is 1. So we'd be left like 2x to the 1, which is just 2x. And e to the x over 2x. Now if you plug x equals infinity into this, you end up with e to the infinity. We're just plugging in x equals infinity, seeing now if we can use just plugging in e to the infinity over 2 times infinity, because it's 2 times x. And that's just e to the infinity is infinity, and 2 times infinity is just infinity. So this does not work either. We have to use L'Hopital's rule again. So we're going to differentiate with respect to x this, e to the x prime, and over 2x prime as well, and see if this time we'll get something that if we just plug in, we'll get an answer. E to the x prime is just e to the x, and 2x prime is just 2, because the x just goes away because it's to the first power. So we get e to the x over 2, and if we plug in x equals infinity, we get, e to the infinity over 2, which is equal to infinity. Yeah, infinity over 2, which is just infinity. So our answer is infinity. It goes to infinity. Okay, let's do another example. So the limit as x goes to negative infinity of the natural log of x over x. And I'm not going to show it this time, but you can tell that it doesn't work if you just plug in x equals negative infinity. Natural log of the absolute value of negative infinity is equal to the natural log of infinity over infinity, and the natural log of infinity is just infinity over infinity, and that means L'Hopital's rule applies. So now we have to differentiate with respect to x, both the top and the bottom. And if we do this, we get the derivative of the natural log of the absolute value of x with respect to x is just 1 over x. I'm just going to write it like that because this is at the top of a fraction as well. Over x prime, that's just 1. That's just 1 over x. Now in this example, we only had to use L'Hopital's rule once. 1 over x, and if we plug in x equals negative infinity, we get 1 over negative infinity. And that's just equal to 0. The denominator is like super strong and just 1 can't beat it. So the answer is 0. Its limit approaches 0 as you go to negative infinity. Okay, well that's pretty much it. Thank you for watching.